Herkese tekrardan merhabalar.
Hi everyone, once again. We are here at the Renewable Energy Systems fourth session of the academic day. We have very prominent speakers from ODTÜ Günam. We have Professor Dr. Turan and the METU Director of Center for Wind Energy Research, Professor Uzol, and METU Director of Center for Energy Storage Materials and Devices. I would like to welcome you all. First, I'd like to briefly introduce Professor, our first speaker, Turan. Turan completed his undergraduate and graduate degrees at Metaphysics Department in 1985. In the same year, he completed his doctoral education in the field of physical electronics at the University of Oslo in 1990. He did postdoctoral research at the Linköping University, Sweden. He returned to METU as a faculty member in 1991 and has been in the position ever since. The main research topic can be specified as semiconductor materials, device physics, and solar and cell technologies. He has directed and continues to manage various national and international projects. Professor Turan worked in the METU Central Laboratory project supported by DPT. Later, he managed the Solar Energy Research and Application System UNA project, which was also supported by State Planning Organization. Central Laboratory and UNAM have become centers of excellence, serving nationally. At METU, Prof. Turan is continuously duties as chairman of the UNAM Board of Directors. Today, he will give us a speech titled Solar Energy Technologies. Thank you very much for the introduction. Hi, everyone. It is, I hope that it's been an enjoyable evening for us. It is the weekend. I'll talk about solar energy and I'll talk about the solar energy technologies. I have a presentation. If you want, I can share my presentation with you. Have I shared my screen? If you can see your presentation full screen. Yes, now, Professor. Hi, everyone, once again. Today, I'll give general information about solar energy, and I'll talk about solar energy technologies. And I'll talk about UNAM, the Research Center of Solar Energy. The energy demand in Turkey and in the world, and also energy demand and supply of energy demand. I'll tell you the place of solar energy. Then I'll talk about the technology part following that. The energy demand of the world is increasing, ever increasing, and we see that here also we use more and more energy, more electricity, we drive more. The energy demand is increasing, and this is a problem that we can see. And the problems, because of the increasing energy demand, there are many problems. There are problems regarding climate, economic problems, and also it is about the future and the peace and the presence of the world, existence of the world. There are a lot of problems in this regard. I'd like to touch upon some of these. The world actually is covering energy demand through fossil fuels. And here upon, as you can see on the right-hand side, there is petrol, oil, gas, and coal. They cover 80% of the energy demand of the world. And of course, there is some needed, and there is an increasing renewable energy resources. when we use the fossil fuels, it's a problem because when we use the fossil fuels, there is a more and more carbon dioxide emission to the atmosphere, and the carbon dioxide causes a heating of the world because the sun beams are enclosed there, and therefore there is huge climatic changes, and there are many natural events as a result of climate change. You can see some of them in the photos. The ice is torn, and in the last season there was both floods and fire outbreaks, and that is the result of the climate change. Drought and aridity is something that awaits us, and for our country there is a huge danger of drought. However, for covering energy need, when we look at the resources that we can achieve, there is the energy source coming from the sun, and it is thousands of folds of the normal energy resources. This shows that there is the other ones you can see, and the sun, the yellow of the circle represents the sun. So all when you compare all of this, it is less than the total energy, total solar energy. We see 17 terabyte watts is the annual consumption of energy. So we can say that there is electricity. If we can transform it into electricity and other things, so we don't need any other energy resource. So this is a very good analogy. All the coal, oil, and gas total is equal to 20 days of sun rays coming from sun. So we can say that the sun is solar energy is a clean and infinite energy. When we say energy, what we have to think of the cost of electricity energy, because all the sectors and this is the main parameter. It is the energy cost. We say it is a cost, a levelized cost of electricity in terms of electricity. And as we can see on the left hand side, there are you can see electricity cost from different resources. The sun one, the yellow ones are from the sun, and the other ones are from the different sources. And in the vertical part, it is a euro cent. This is a calculation for Germany, which is made in the last June, and this is the one. The ones actually are less than the cost of the other sources. So there isn't any argument of solar power is expensive, because in the recent years, of course, it depends on where you are in the world, but the electricity energy from that is the least cost one, and under certain conditions, so we can say this, and the solar energy systems are increasing, as you can see in the world. This is the total power, and we can say that in 2010 it is 150 gigabyte, and it is now 1 terawatt. As we can see, the system, the total installed power of the systems using solar energy. So it is above all the expectations. So when you look at the past projections about the future, we can say that the figures are far beyond that projected figures. The solar energy is a very cheap energy. As you can see, another indicator. In the international markets, there are the tenders, international tenders. One was conducted in 2021 in Saudi Arabia. Saudi Arabia's second PV tender draws world record for low bid of for $1 per kilowatt per hour, watt per hour. It's a very low cost and it is almost free of charge right now. And in Turkey last year, a few months ago, there was a new tender and the price was $2 kilowatt per hour. So to make a comparison, I can give you for Akkuyu nuclear power plant is to $12. So we can say 6 folds of the figure that you see here, and this is going to be paid for 15 years. So I can tell you that the solar energy is now very cheap, and for countries like us, it is one of the most important factors and options. And of course, there are bigger tenders, as you can see on the left-hand side. These are the tender prices. And in Portugal, 1.8, and in Qatar, $1.75. And this is energy type that covers all the world. And in this tender, we say that there is a $7, 1,000 megawatt tender was given in Konya Karapınar, which is the construction is still ongoing. Half of it has been completed. It will be one of the largest central power plants of the world. There are many power plants. As you enter into internet, you can see that it's more than 2 gigawatts. For example, there are larger power plants, and this increases day after day. The total electricity share, when we look at this by the countries, there is an ever increasing ratio. It is a 9% in Germany, in Israel, in Chile, in Australia, in Greece. It's more than 8% in Turkey. Turkey, it's mistaken. So we are like 5%. It is now 4.5% in Turkey for the solar energy, for the solar energy cost. The total PV photovoltaic capacity is 7,300 megawatts. And we can say that it means 11.7 terawatt per hour per year. And we can say it is 4% among all the other costs of energy. The solar panels cover large areas, as you know. These large areas are not as much. When you look at the red dots here, you can provide, you can have installed the power plants covering all the energy demand of Turkey. So in Turkey and in the world, when we make a calculation, so the ones when you cover such a land, you can produce all the electricity energy demand of Turkey with the power plant that you install. So we can say that the area that is not as large as you think, and of course the roofs have a potential, are creating a potential, and of course coating this roofs will create an important potential. So we can say that the solar energy is clean, infinite, motionless, silent, non-owners owned, and accessible, flexible, and cheap alternative. And we believe that there are some observations about this solar energy will be an important energy type, and it will increase. It is on the increase, and it will increase even more and increase its share even more. So as a result, the grids and the networks will be eliminated in the future. There will not be huge grids and networks. So there will be for small communities, we will use smaller ones, and this is an important advantage. And we don't have to transport energy from one place to another. So in the speeches, there were some speeches, and the sun, solar energy, wind energy, and the storage of this. When you gather these together, you don't have to have a big dams actually. So Ahmet Zaki Yamani, he was very popular minister. He says that I'd like to quote from him: "The stone age did not end for lack of stone. The oil age will long before the world runs out of oil. The oil age will end long before the world runs out of oil." This is a saying from years ago, and it's about the we can expect that oil wells will be closed because of lack of demand in the future. We don't think this is a dream, and of course the European Union and when you look at the developed countries of this when you look at the Paris Convention and similar applications, there is the progress in this regard, and European Union and in the other countries, the use of fossil fuels decreases. For example, the European Union by 2030 will close down all the coal power plants. So I'll talk about economy and politics, and I'll talk about the technology. Let's look at the sun. The surface heat temperature is 6,000 Celsius degrees, and it increases 15 million centigrade in the core. There's a 200,000 ton hydrogens. So you don't have to be afraid, but it has a life cycle of 4 or 5 billion years. And the power is 63 megawatts per square meter. In Turkey, the power comes to the world is 1,353 kilowatt per square meter, and we can use this figure. And when we look at the spectrum, you can see on the left-hand side of the graph, you see ultraviolet, the red part, and we can say that this the infrared technology, and the green is where we are. This is the seeable area, and this is for the 400 of years. People adjusted their seeing eyesight for that for the sun rays coming from sun. So we can say that this is the largest one. Of course, there are some losses in the atmosphere, as you can see, but this red area is coming to us to our to our world. You can use photovoltaic systems, as you can see, or you can see focused heat solar systems. There are two systems that you can have electricity out of solar energy. There's parabolic ones or tower type one. In photovoltaics, there are some applications, and there are flexible applications as well. When you look at the photovoltaic systems, and there are different technologies there, and there are 4 main areas. And we see crystal ones, so we can see, and you can see the other ones, and this goes up to 40%. It increases, and there are new opinions, and when you look at the market share, you can see crystal silicon, and it says it is less than 5%. It is written wrong here. The others are more efficient, but they don't have a huge market share because of the cost. The cost is a very important factor here for crystal silicium technologies. We can say that it covers all of the markets right now in the world, and in Turkey, it is the panels used in Turkey. It comes from crystal silicium materials. In the first 1954, this was found in IPM Bell laboratories. And when it was first found out that the efficiency was 2%, it was priced very high. However, it started using satellites in the space, and it's also outgrowth of space exploration in the upcoming years. A photovoltaic cell, a solar cell, is actually different from the other energy producers because it doesn't have a mobility structure. It is a stationary structure in a plate, and there are differences there. You can use a part of this for different electronic properties, and the other part for different properties and characteristics. The electrons absorb the meal, and they turn the curve. It's like a water coming from the dam, and it's pumped to one part, and it goes, it outflows, and here there is electricity current here. We call it as a photovoltaic solar cell. You see a cell produced. They are 0.5 to 1 volt current, and you can gather as many as possible, and you can have large or small scale plants, and it is a motionless and a silent system, and it is discriminated from the other energy, differentiated from the other energy resources. Electrons are on one side, and they are outflow of the material. There are crystal silicium solar cells are monocrystal, multicrystal, and heteronuclear crystal. I don't want to go into details of some of them are more efficient, but there are different technologies and different aspects. And in the films, for example, they can be transparent, and in terms of construction technologies, that could be some interesting applications. Thin film panels are there. There are different applications. So you all see that, for example, stadium, the satellites, the swimming photovoltaic effluent systems, and also on the buses and everywhere. You can increase these applications even more. This is METU Northern Cyprus campus. There's a 1 megawatt, and it contributes a lot to the Cyprus electricity demand. And this is one of the projects completed by METU. This is a 6 megawatts photovoltaic power station, and all of these panels are produced domestically in Turkey with a TÜBİTAK and a company with it's the project conducted by GÜNAM. So I'll talk about GÜNAM. It's the center of excellence, and it turns solar energy into electric energy and heat. And here in 2009, it is officially established with different periods. It received support from different parts of it. That we first take it from the DPT State Planning Organization, from the Ministry of Development. There are many European projects, and there are national and international projects. And since 2021, it will be separated from university, so it will graduate from university, if I might say so, and it will be an autonomous research center under the state. Of course, there are some objectives, and these objectives are very assertive. Once the objecting gets the new, one of the few research centers in the world, prominent centers, and this is a new logo. This is a logo that we defined as a result of a competition. And we have very bright academicians, and there are people who had their doctorate in different PhDs in different prominent universities. Some of them are full-time, and some of them spend time in university, and some of them spend their time with us. We have many students supporting our active studies. As you can see, this is the Günam building. It's an operational building, an active building, and it is in use. So there's industrial research here, and as you can see, and on the left-hand side, you see in the campus, it's one of the pioneer studies. It's the METU Research Park concept, and in one wing of this building, or the Günam will be there, but the building has not been completed yet. It will be completed until the end of this year, as we expect. And you can see the building, operational building right now. It is like a pilot manufacturing facility. We have the machines which we can create the solar cells, and of course they're smaller than the plants. But anyone, you know, it's a facility with the right qualifications. It attracts attention from the larger companies, and we conducted some research activities with different countries. We have 6 technology units: holistic photovoltaic, developing photovoltaic. This is for the newly developed materials, and there is panel technologies, power electronic and system integration, and the thermal power and test and characterization. We have 6 units, and this is all from my side. And I think that I had 24 minutes of time, and I have completed the time given to me. And if there are questions, I'd be happy to take them, and I will try to answer the questions. So we will get the questions at the end, then. And that will be a closing. Now I would like to give the first to Oğuz Bey, and I'd like to invite him. I would like to briefly introduce Professor Dr. Uzol, who will be with us with his speech titled Wind Energy and Wind Turbines, and then I leave the floor to him. Professor Dr. Uzol received his undergraduate and graduate degrees from Aeronautical Engineering Department in 1992 and 1995, and respectively. He received his PhD from Penn State University in 2000. He worked as a postdoc at Johns Hopkins University from 2001 to 2005. He has been working as a faculty member at METU Aerospace Engineering Department since 2005. He has been the founding director of METU Wind Energy Technologies Application and Research Center since 2011. Now I'll give the floor to you. Thank you. I'll share my screens.
Raşit Hocam, can you kindly turn off your mic? Thanks. Can you see my screen now? Not yet. Yes. Thank you for your kind introduction. I will talk about the wind energy, which is another renewable energy similar to solar energy. And I will also talk about wind turbines technologies, and I also we'll talk about my center. Why wind energy? Because it's a renewable energy. When we say renewable, we mean it is an energy that we can use it. And the cause of the wind is the sun, and there is this air flow. And as long as the sun is there, there will be airflow, and we will be able to use it. And it costs no fossil oil, and we are using nature. It's a common and redundant resource because unlike some other resources, it is equally distributed and it is available in all parts of the world. And it is clean. That means there is no CO2. There is no fossil oil burning. That means it is quite clean. Of course, since it reduces being dependent on fossil oils. As Rashida just stated, Turkey and many other countries depends on fossil oils. But in our country, we do not have enough fossil oils. This is why we have to increase the portion of the renewable energy. It is important for the independence of our country. It is the case for all countries. It is not a new idea that the wind energy is used for people. And at that time we had, for example, the agricultural activities that are carried out by windmills, and it was introduced to Europe, of course, thanks to the science and technology developments. This design was considerably improved. So not only for grinding, but also it was used for water purposes. As a result of the discovery of electricity, and some people discussed whether it is possible wind power should be used more now for the electricity generation, because electricity was quite new at that time. And he thinks that he wrote an article to defend and promote the use of wind for electricity production, electricity generation. In order to use it efficiently, we need to understand its basis, its fundamentals in a clear way, and the power that comes from the wind is important. There were some experiments, and as a result of these experiments, 3 main outcomes were found. If there is a mechanical, you need to have direct proportion between the fan and also the wind, and the torque on wind, it should be equal to each other, and the power that you generate should be equal. The maximum torque and the maximum power are equal to wind speeds square, and also the maximum power is equal to wind speed cubic. So these are theoretically proven data. Since the early 90s, electricity was discovered, and the wind turbine that was used to generate electricity is shown on the screen, and it generates 12 kilowatts in 1888 in Cleveland, Ohio. Today, of course, in the course of the years, there has been an immense change and also developments until 1990s, from the early 20th century to 1990s, there were lots of developments in this field. And this, in order to clarify megawatt and kilowatts, I will talk about this issue later, but it was not cost efficient until 1990s, but especially the developments in the airspace technology and also generators and this aviation technologies. Towards the late 1990s, the wind turbines became cost-efficient systems, and they became attractive investment fields and investment areas for investors. As you see on the screen, it is a wind turbine and that generates 3 megawatt. That means 3,000 kilowatts. So it looks like, especially on power plants on the surface, its size, it is, we do not call it fan, we call it rotor, and it is 103 meter, and its height is about 150 meter. When we look at this, we have this rotor, the winds, and also this nacelle, which has this electronic systems, and also the motor is there. And in order to get an idea about its height and its size, the Atakule, which is one of the symbols of Ankara, those who are living in Ankara will easily notice, or you may know this symbol, it is 125 meter. And so wind turbine is such a big structure and construction. It is 150. Next time when you see the Atakule, you will get an idea about size. As I said, these 3,000 kilowatt turbines are not the biggest one, because there are bigger wind turbines, especially those which are mounted on seas, and we have big turbines there. For example, this one is a wind turbine that generates 6 megawatt. And as you see, there is a plane, and it is the biggest plane in the world, and you can get an idea about its diameter. And it is Airbus 300 and 800, and even the biggest airplane in the world can pass through its diameter. Why it is important? Because in the design of wind turbines, and we face many problems as a result of this size. We have many wind turbines, and also it's the power plant. And next time when you see another wind turbine, please try to follow the wing with your eyes, and you will have difficulty. You will realize that you will have difficulties in following, because although it seems it is slow, it is not, because its speed is 340 kilometers per hour. Even though it evolves, it's around in a slow motion, it is too fast for us. And for all wind turbine elements are connected to each other, and I will talk about some other elements later. So far, it is 3 megawatt wind turbines. But what does it mean for electricity generation? How it generates electricity? Because it's continuously evolves, and let's assume that it works in its full capacity for a year, and it has a potential of 26,280,000 kilowatt hour. So it is not big comparing to electricity power plants, but of course there is no wind in some days, and there are some changes according to the seasons, and there are fluctuations. So in the worst case scenario, we estimate that there is 30% loss in its capacity. That means this turbine generates 7.8 million kilowatt hour. Okay, it generates, but what does it mean in our daily life? A nucleus family consumes about 5 kilowatt hour, and if we calculate it by 365,000, a typical family consumes 2,000 kilowatt hour per year. That means 400 houses will use this capacity, and it's a rough estimation, because as for the investment, there is need for a detailed estimation and calculation. So how many wind turbines do we have? We have 743,000 megawatts capacity. That means 976,000. So it is 976,003,000 houses. 3,002,000 houses. And what about the situation in Turkey? We have 10,000 megawatts. A few weeks ago, we have reached this 10,000 threshold, which is very important. There is a new plant in the far east of Turkey. It is in the city of Van, and now it is 10,000 megawatt, and the total capacity is 10%, is equal to 10%. And as regards to the electricity generation, the wind turbines make contributions about 10% of the total electricity production. That means about 12 million houses can use this capacity. And you can see the development in the course of the years in all over the world, from 2001 to 2020. And we see the curve, and the bars in green show the total power, total capacity of the wind turbines, and at the right hand we see 7,043, and the difference between this amount and also the total one, and the blue part shows the plants, power plants, the wind turbine power plants on the seas. And what we see that during the last 15 years, according to research and several projects in the United States and in the EU and in Far East projects, this technology develops a lot. That means these power plants on the seas become cost efficient. That means there will be an acceleration in these type of power plants. What we see that for a decade, from 2008 to 2018, there is this curve in 27 EU countries, we have the European countries, and we have this capacity. And the blue one, is showing the wind, which shows, and the yellow one is the sun, which is in dots. And while the trend of the wind turbines and also solar power was not so high, what we see that they are making progress and they are gaining more space. And according to this chart, what we see that as of 2020, what we see that for the first time in the history, renewable energies capacity is more than the amount of the fossil oil energies. And when we talk about renewables, I refer to solar energy and also wind turbines, and it is the wind energy atlas. And we have mainly the Aegean part, the northern Aegean Sea region, and also Marmara region are the areas that we have high potentiality here. And also in central Anatolia, we have some parts that have high capacity, especially since mid 2000s. The first one was established. The first wind turbines was established in Alachate in 1998, and since then we have established many other wind turbines. And this map shows the wind turbine power plants across the country. And what we see that there is a concentration in the Aegean Sea region and also Marmara region, but we know that there are some other power plants in different parts of the country, especially in the Anatolia. So let's talk about the technological part. The wind turbine generates power. In the beginning of my presentation, I said in the 1700s, there were some experiments, and the electricity that is generated by the wind turbine, it is equal to the cubic meter of the wind turbine. But what we see that the left side shows the power that you generate, it is kilowatt, etc. And the right part shows how you generate these energy. There are some other parameters. For example, there is this parameter called rho that shows how you generate it. And this rotor part, that we call it rotor, and shows its square meter and its area. And also we have this wind speed, and it cannot be more than 0.1593. So density is important, and we know that the wind is dense, especially in the seas, and the rotor area and the higher diameter means, and also of course it means more energy is generated, and also the wind speed is important. For example, if the wind power is doubled, then your production, your generation, your energy generation becomes 8 times more. These turbines uses this power curve, especially for the commercial purposes. It shows the wind per speed and also the power that you generate from the wind. And it begins the cut in wind speed. And even if the turbine evolves around it, it does not generate power. And we have this rated power wind speed, and there is this generator on it, and it is the highest level of the generator. It is 3 megawatt, 4 megawatt, 5 megawatt. And when it reaches there, and when the wind power, even though wind speed increases, it is unable to generate power because it already reached its full capacity. And what we see that it is the wind speed and also time. So X shows the speed and Y speed shows the time. But is it the real case? Is it the real scenario? Unfortunately, this is not the case. Because if we use this scheme, that is the reality. It was recorded for a year, and this is the real data of wind. Of course, it is related to the size of the turbines as well as all other parameters that are subjected to the variables. And this is what we face from the engineering perspective. For example, the speed of wind may easily increase or decrease in a second, in a minute. So in such a fluctuating speed of wind, what we see that we need to have machines that are resisting such changes. So it causes two types of problems. First, the change in wind power creates some difficulties with calculation of the potential energy generation. And the design of wind turbines is not an easy task. It is not, you just see the winds. Even the wind turbine wings design is difficult because there are shafts, there is power, and there is tower, and also wake turbulence, wind shear, extreme wind. These are the issues. Even for the wings, we work very hard, and there is need for research, tests, and also there is need for efforts. Therefore, we need to find solid and also the cheapest wind turbines, because wind turbine market, as Professor Rashid stated, it is cheap for solar power and there is a cheap price for wind turbines. So it is considerably competitive and it costs a lot, and they need to develop technology. In the 80s, if you were manufacturing small size wind turbines, that was the wing. And if you don't have the technology, they ask if there's an order to generate 5,000, not 50, that will be the size of the wing. But is this the case for the real one? No, it looks like this one. If you order a wing for 5 megawatt energy, so it is light and its design is sophisticated. So my last a few minutes, let me move to the topic of our research center in the light of the pact. RUSGAM, like as in the case of UNGAM, it was established with the support of the state, and it is our 10th year now, 10th anniversary. We are working very hard, and we still get support from the state, from the government. We have three main areas. We work on the wind potentiality and also airflow over topography, and we have wind we have wind turbines technologies, and also we have socioeconomic impacts. And all these issues are our topics. And also, we, as in all other engineering cases, we have groups that cover these issues. We have three main objectives. We aim to provide services to the community, and we aim to serve to the community as regards to research and development tasks, training services. We also aim to train human resources and capacity, and also raising awareness about all these issues. As I said, we were established back in 2011. All relevant units supported us at that time. We have become one of the well-respected research centers in Europe. Of course, this state planning system, now its title has changed. It has become the Presidential Office Planning System Office, Presidential Office Planning Bureau. And these infrastructures, we are working on the wind tunnels. It is one of the biggest tunnels in Turkey. We began working in 2014, 2015, and we worked for design phase part, and then we moved to the public bid phase, and it was constructed until 2012, and now it serves for the testing purposes to the industry since January 2021. And these wind turbines has different testing stages. So it is not only the wind turbine sector, but also there are several other sectors that need these testing services. This is why and how we designed. So far, we have worked with many defense industry companies when they need these testing services, especially the wind turbine manufacturers join us, and also the construction sector also uses our center for their testing, for wind tunnel testing services. And we also need to train staff who is capable of doing everything. And we have MA and PhD students for this program. That's all from my side. That's the end of my presentation. I'm happy to answer if you are here. Thank you. It was a very informative presentation. I took several notes. As I said, we have some questions, but I will ask them to later. Now let me move to Mehmet Hoca. The last panelist of our session is Professor Dr. Mehmet Kadri Aydınol. He has been working in the Department of Metallurgy and Materials Engineering, and he is also the director of METI Energy Materials and Storage Devices Research Center, ENDAM. Dr. Aydınol completed his PhD study at METU Meteorological Engineering Department in 1994. Subsequently, he went to the USA to the postdoctoral study at the Massachusetts Institute of Technology, Department of Material Science. His work on Li-ion batteries has been first started there in 1995. His research interests include the synthesis, characterization of modeling of materials, especially for energy storage and conversion applications. In this context, he conducts material development studies for Li-ion, alkaline, zinc air batteries, and supercapacitors. He also carried out joint projects with the industry and on device applications. Electric vehicles and grid energy storage users are predominantly involved in device applications. He is the co-author of nearly 40 journals in prestigious journals such as Nature, and cited more than 2,500 times according to Web of Science. He holds international and awards. Now the floor is yours. Yes. Thank you. Let me share my screen first. Can you see my screen? Yes. Thank you. I will talk about the electricity energy storage. Why do we need to store electricity? Electricity energy, because it is not similar to water. When you close the gate, water waits. But this is not the case for electricity, because even though you turn it off, the electricity unfortunately does not wait for you because it's consumed. So the grid level and the storage of this energy, because the unused electricity is lost. What kind of advantages do we have when we store it? Because it might be at various levels, at the grid level or distribution level, or even at the house level. So since it provides these alternatives, it is important. What kind of advantages does it have? Of course, it is flexible. So although I'm not an expert of electronic, we know that this type of storage capacity increases the capacity, and also it improves the efficiency, and also it facilitates the order part, and especially in the southeastern part, in the south part. And it is important to manage this part.
And thanks to these applications, we are able to provide certain alternatives to energy users. As for storage in renewable energy sources, here, solar, wind, yes, we want to make use of these sources more so that we don't burn natural gas or coal, because the biggest current account deficit of Turkey is run because of the natural gas, and we use natural gas mostly to generate electricity. So if these renewable energies increase in amount, our country will gain more from it. However, we do not see any continuity or sustainability in these sources, as also explained by Professor Rashid and Oud. And of course, there are changes in sun and solar. So if we can generate electricity, we can store it. Otherwise, we can give the energy back to the grid. Similarly, in such resources, unfortunately, we encountered this situation, although I'm not an expert on this. I hear it from the experts that when the renewable energy resources have more than 20% share, different issues are encountered, like the differences in frequencies. So if you can store actually the renewable energy, then you can increase its load on the overall system, as it provides frequency regulation, and it also serves as an emergency state reserve. Actually, we see that not just in power plants, but rather in other factories working in the industrial area. So such battery storage systems, or generally energy storage systems, can be maintained as such. What kind of technologies do we see? First, electricity energy storage, where capacitors are used actually commonly, and also superconductive magnetic energy storage is one of the techniques. Also, mechanical energy storage is another method. And here you can use pumping technology, pumping hydroelectrical systems, and also you can ensure that the condensed air can be used for energy storage. These are used widely in Turkey. There are certain pumping projects in Turkey. I will briefly refer to them. Another energy storage technology is related to electrochemical energy storage, where we have batteries. I'd like to say a few sentences for each and every one of them. Chemical energy storage is mostly based on the generation of hydrogen, where water is separated into hydrogen and oxygen. With electrolysis, you can store that hydrogen, or you can burn that hydrogen and actually get heat. Also, you can give it to the natural gas plants and decrease natural gas consumption, as it does not consume carbon. So it provides a more environment-friendly approach. And the third one is the thermal energy storage. I will here refer to electrochemical methods or practices mostly. But when we look all around the world in terms of these technologies, we see certain scenarios. According to these scenarios, they have certain estimates, and for estimates until 2030, they say that the energy storage sector will grow by 31% cumulatively on an annual basis, taking us to 741 gigawatts of energy. It's not that high as we speak today, but as the graph shows, according to 2019 data, almost 93.4% of the stored energy is provided through pumped hydro energy plants. When you look at the other slices, you see actually small shares, like 6 to 7% electrochemical storage, and the other one is still small. If you elaborate on electrochemical storage, you see battery-based storage with Lithium batteries having an 87.3% concentration. This is a 2-year graph, or a graph dating back to 2 years ago. However, as we go to 2030, we will see a growth in electrochemical storage technologies. And according to the estimates, the electrochemical related storage capacity will be 20 to 40% bigger than what we have today. And pumped hydro electricity storage will decrease a little more, while the other technologies have more weight. The world definitely needs to store these energy sources, especially in renewable energy, because we have day and night differences, which actually is a hindrance to continuity. So if you can store the amount of unused electricity, then you may actually make use of it when you need the next time. Pumped hydroelectrical energy storage is another system, and it helps 90% of the energy to be stored. In Turkey, we have a 4 to 5 years history with these dam. And here the working principle of the system is very simple. You need an elevation difference. So if you have a water resource like lake or sea, you can use pumping turbines, and you can actually send the water to a higher elevation. And here, this is both pumping. This element is a pumping and turbine device. There are plenty of examples in the world regarding this transfer, and 90% of the energy is stored like this in the world. And according to current figures, China has an installed capacity of 30 gigawatts. In Japan, we see a similar number, and we see quite a high number in the US. As I said, there is this ongoing initiative in Turkey, and it has an advantage. According to a study, Turkey is said to have a potential for installed capacity of pumped hydroelectricity energy storage, which is higher than all around the world. Our topic is maybe a little different, renewable energy systems, but I wanted to emphasize this potential as well. When we look at the energy storage technologies, actually power is a parameter in terms of storage. What power do we need, and for what duration do we need? We need to ask these questions. And when we look at the practices, we see voltage regulation, frequency regulation, or balancing of power in renewable energies. And here we need actually durations of minutes and days. And the expected powers range from a few kilowatts to gigawatts. So this range is a critical range for us. When we look at the other areas, we see seasonal durations like 1 month, 2 months, 6 months. If you want to benefit from the energy for that duration, you need more different technologies. But as we look at the current ones like super capacitors or flywheels or batteries, you see batteries within this range covering actually the whole, almost the whole range. Pumped hydro is about a huge lake or reservoir, which will be able to provide you with energy for a longer term. That's why their usage areas are mostly related to seasonal storage. When we look at the batteries, the used battery technologies are related to the chemical substances, and the battery techniques show that actually were used even a few centuries ago on the Volta site. And even there's this famous drawing just before the Napoleon. He chose the battery he designed by himself. But when we come to the current day, we see dozens of varieties. And I try to emphasize the batteries with a focus on storage. And zinc-based batteries are one of them. Lead acid batteries also represent an established technology. And Leon batteries cover a huge area, both in terms of rated power and usability. Also, sodium batteries and flow batteries can be briefly mentioned. These batteries are quite conducive in terms of storing the renewable energy generation. What are batteries? What are their basic principles? Let me very briefly refer to that. There's this anode and cathode ends, poles, and here you see a downgrading reaction. And when you have this charging of the battery, you give 2 electrons, making it ionic with zinc, and it will be mixed to the solution. It will follow this path, reaching the cathode, and the copper ions will get in a reaction, and the zinc will get dissolved here, while the other one gets power. These are called Fredox reactions, and they create potentials with oxidation. These are known constant values under standard circumstances, the oxidation reaction of zinc is 0.76, and that one in copper is 0.34. When you add up both of them, you achieve a voltage of 1.1, which is something to do with thermodynamics. Many elements and substances can be used, and actually you can find all these tables in textbooks in terms of reducibility potentials or reduction potentials. Here you choose a couple of elements. For example, lithium is the most electronegative element. It is a very low level, and fluor has the highest value with 2.87. So if I can produce a lithium and fluor containing battery, the total size will be 6 volts. Of course, this is the theoretical side. There are practical difficulties, and the reaction may not take place as expected. But by taking into consideration these reduction or reducibility potentials, you can create many batteries, and dozens of them, as I told, were produced earlier. I showed the important ones. Primary batteries here mean that you can use them only once. You cannot recharge. You just dispose of them. Zinc, carbon, manganese oxide actually has an old history, maybe 100 to 200-year history. Manganese oxide, it's not used that much, but there's another version of it. Now, electrolyte is used in alkali form rather than the chlorine form, making it more effective. So the disposable batteries, as we know, called 2A or 3A, are generally made from alkali, zinc, manganese oxide batteries. Also, there is this organic electrolyte with lithium manganese O2. We use all of them and dispose of them. As for the secondary batteries, these are rechargeable batteries. The oldest version is the acid one containing lead, so lead acid, and we used it in our cars. It has one of the biggest commercial values in the world. Zinc, silver oxide, nickel, cadmium, nickel metal hydride, and lithium ion batteries are all used in consumer electronics cars. And the most common one of the most common technologies is the lithium ion or ion batteries. What kind of systems are used in energy storage systems, both for grid and renewable energy? I'm not going to talk about mobility much here, but when you look at the big scale systems, you see the traditional ones being used, and lead acid is one of them. Again, there are also batteries working at high temperatures and lithium batteries, and also there are flow batteries. I will also be returning to them very shortly. So these are all the battery types. Okay, what is ion and how does it work? Here you need anode and cathode, and here you have to store lithium either in a metallic form or in a store. Unfortunately, it contains huge times to store it in metal form, going back to 3 decades, and graphite and other lithium compounds were used later on. However, as we look at the current studies, there are R&D projects focusing on a return to lithium in metallic form. Lithium gets oxidized and gives batteries. It goes around this circular circuit, and reaction takes place. What do we use as the known brands? We get carbon oxide or lithium iron phosphate and NMC and NSA are part of them. Negative active substances include graphite and also lithium stearate and other compounds together with actually Si. And here in lithium ion batteries, we see 300 watts are per kilogram. And here the target is 400 watts, and that can happen with the development of new materials, nickel, manganese, cobalt, or this compound have different properties. Unfortunately, there is no ideal scenario for them. Some come to the forefront with certain properties and others come to the forefront with other characteristics. NCA is mostly used in the automotive industry due to their high energy density, and they actually provide you, for example, ranges of not 10 kilometers, but 100 kilometers. But security is also an important component. You see exploding batteries or cars that catch fire. These are also critical issues. And there are serious projects searching these aspects. Lithium, that's why lithium iron phosphate is used especially for systems that require high scale batteries. I mean, one battery might explode in a mobile phone and not cause much damage. But if you think of a actually bus, there are hundreds of batteries there. Now Tesla used to use NCA, but it's giving up on that and now establishing this factory in China, maybe due to economic reasons as well, as nickel and cobalt are expensive. But lithium iron phosphate actually now is used more. Of course, here there are certain challenges before the use of lithium batteries, especially in terms of energy storage. That's why we should ensure thermal control and packaging in these systems. Also, we should pay attention to excessive charging sensitivity of these products. I do not mean to elaborate on all these details, but lithium-ion batteries sound indispensable today, but we need to be very cautious about them. Wrong engineering may actually lead to very big accidents. And when compared with other batteries, there's this cost element. When they were put on the market by Sony in 1980s, 70s, 80s, their cost was actually $1,000. Now for 1 watt, now we are talking about 200 watts, both through enhanced production technologies and improvement in the production itself, but still it sounds expensive, but we don't know what awaits us for the next 20, 30 years. And actually, it may cause a serious concern because the electricity cars say we are arriving. The story starts back in the 1990s, but we also had actually a buzz in 2010 after 1990s. We see another buzz trend in that development. And now the big manufacturers do not view the issue as they will continue to use oil. There is this serious, keen interest in batteries and storage, and it is expected that 2 terabytes of energy will be required by electricity cars by 2030. How lithium ion will meet these needs, or how the sources in the world will meet those needs, of course, is a matter of question. We see commonplace practices of lithium-ion batteries, as I showed in my previous slide, there are significant investments here. Now, the systems used for storage in conventional electricity investments was around 10 megawatts. But however, we're near gigawatts as values now with the newer facilities, and lithium is used there. For example, Tesla has this mega package, a package with 7,000 units of small batteries and 142 again Tesla mega packages are used. It has a power of 100 megawatts. It's one of the biggest again in California. It has a 1.2 gigawatts of energy and 300 megawatts of installed capacity, one of the biggest in the world actually. China didn't come to play yet. It's on the way to establishing the biggest facility with installed capacity. And it's another example in Australia, installed by Tesla batteries. This one is a mixed project benefiting from both solar, wind, and battery storage. So lithium-ion batteries are becoming more and more common in all the countries. And with the maturity of lithium and high number of manufacturers make things easier. We do not foresee a very huge bottleneck, but of course there are we need to make certain predictions for the next 2-3 decades. Another technology is lead acid, a very old technology, but also developed one. Unfortunately, the lead is heavy and it leads to a low mass energy intensity, around 30 to 40 watt-hour per kilogram. We say that lead is toxic and it harms the environment, but these actually battery systems can be recycled 100%. Even 1 grams does not get mixed in the environment. So it would not be wrong to say that they're environment friendly. An issue though is that they have low cycle life. But now we have an ultra battery where actually carbon and lead is used mixed, and the cycle can go all the way up to 5,000. In the past, we used to see more examples of lead-based storage systems. That's not the situation today, but there is this 250 kilowatt ultra battery energy storage system in the US. Also, this solar park example in Germany has an installed capacity of 2 megawatts. These are all lead-based. It's heavy, but we do not transport it to any other location. It's not a huge issue. It is not going to be used in vehicles, as they will not be able to carry it, but the lithium will be quite concentrated here for longer years. Another battery type is high heat battery, nodium sulfur and nodium nickel chloride systems. These operate at high degrees, between 300 to 350. So all these substances are in molten form. They are in liquid form. Here, azote operates as anode, and actually the other element of sulfur works as cathode. There is no need to elaborate. It was first developed by Ford. It probably had an idea of using it in cars. It is not that conducive for mobility though. However, Japanese NGK commercialized it, and this is the only company producing it in the world. One of the most important disadvantages is that it does not provide much of an economic alternative. You cannot make huge investments with only one supplier, and NGK actually installed a few facilities in Japan. As far as I remember, they have an installed capacity of 30 megawatts. They have advantages and disadvantages. But one of the main problems is that there is one single player. And when that is the case, you cannot make your presence felt. Also, Zebra is another battery module used in South Africa. But despite their implementation in a few practices, they didn't become commonplace in the world. Another battery technology is flow battery. This is quite an interesting system as well. The capacity matters for us, and what determines the battery capacity is the amount of anode and cathode substances, their space filling properties. And here, although you have a small cell where the reaction takes place, you can take these liquids with these pipes and generate electricity. So the liquids here should be redox active, and there are quite redox active electrolytes developed around the world. One of them is alvanadium, where it has +2 and +3 values, and it's called redox and vanadium batteries. Also, zinc bromine and iron chromium are the other two technologies that see actually serious implementations. Flow batteries can take place in these stacks. Anodes and cathodes can be added to each other, and you can actually connect these with serious connections. One of the complications is that it has complex design elements. You need to have pumps, flow controls, and the solutions deployed should be actually considered in terms of the reaction with the cells. As I'm saying this especially for the corrosive ones, but it has also a common application area in the world. There's this 1 megawatt installed capacity in the US. I think this is the biggest flow battery storage system in the world. In Japan, it has 17 megawatts of installed capacity and 51 megawatts per hour. Those gigantic tanks actually enable you to take the liquid and create reactions. Alkali batteries are the ones we already know. These two are not used much, but zinc manganese oxide has an important potential. Actually, it's an old battery type used as a primary battery type, but now they managed to make it rechargeable due to important R&D activities for the past decade. Actually, this has a cheap cost, $50 per watt hour. However, again, we encounter certain issues here, but with intensive R&D, we know we can improve and even eliminate them, and we are working on them as scientists. One of the important problems is that the zinc actually poisons the cathode side, and tyrosine products actually come together, and zinc temperate is another issue. So actually there are important studies going on to overcome these challenges. Supercapacitors are the last topic. They do not operate like the traditional batteries, but we can deploy different supercapacitors. And here they attract anions and the opposite side to the anode and cathode. They behave like capacitors. When you take this load, you are able to generate a very high flows at a very high speed. Such capacitors are used widely, especially in vehicles, heavy vehicles, including trucks and buses, where you need acceleration or increased performance on inclined roads. However, we generally see hybrid applications mostly. There are a few examples where you see batteries and capacitors next to each other. Generally, they do not have high energy intensity, but they have amazing power intensities. That's why when used in hybrid mode, they can present various advantages. Let me utter a few words about NDAM. Energy Materials and Storage Research Center go back in history, but officially our center was established in 2008, and it is supported by researchers from ODTÜ University, Erciyes University. We try to carry out certain activities focusing on sodium ion batteries or lithium ion batteries or alkali batteries, because zinc manganese has a significant future. Flow batteries, zinc air batteries, lithium sulfur. I didn't refer to that much because it hasn't been realized yet, but they present significant potential. Also, supercapacitors are one of our research areas. We check these substances, experiment, and come up with products. So we help the industry both in terms of active component or material synthesis, tests and characterization, and battery and device production. We are supported by researchers in the academia from different universities. Also, the industry shows keen interest in our activities. As you know, electricity cars have been more actively discussed for the last couple of years, and there have been significant investments in Turkey. That's why we position ourselves accordingly, ensuring that researchers and industry people receive our support. This is one of the main activities of NDAM to spread training and science at a grassroots level. That's why we have a symposium under the name of MESKİS, and there is this summer school component of this symposium. We held the 5th occasion of it a couple of weeks ago. Next year will be in Croatia, in the city of Split, and we enjoy participation not just from Turkey, but also Europe and the world. And this enables actually the training of our young colleagues as an umbrella platform, and our door is open to anyone interested. Thank you very much. If you have any questions, I think we can discuss them now. Thank you. I think you can see me now. I also see Professor Rashid. Well, we have run out of time normally, but I didn't want to interrupt you for the presentation of valuable information. I will ask one question for each so that we do not take time from the previous sessions. The first question is for Professor Rashid. Professor Rashid said that the grids will be smaller. In that case, can we say that individual buildings will be more popular? I mean, will we see individual grids for each house? Well, we'll definitely see that, but we reckon that small communities will have small power plants, small neighborhoods, cooperatives, cities will have small power plants. Considering Ankara, for example, we might have 8 to 10 medium arranged plants, of course, operating together with wind. I do not separate sun from wind as an energy resource, because we generally should think of the two in terms of not harming the environment. It is difficult to say the same with the geothermal because there is a serious intervention there. But solar and wind can be considered in combination. Certain districts of Ankara or areas just outside of it will have small plants. And here the roofs are very important. By the way, I'm having one installed on roof of my house. I think we're going to see a wider use of such roofs. There are legislation related issues, but they are going to, I think, be influenced by this wave coming from the deep, and we're going to see a flexibility there. Thank you very much, Professor. I would like to ask this question for Professor Oz, but we cannot ask all other questions. The floating plants, what costs can be a candidate for them? A good question, because as I showed in my presentation, the installed capacity of 10 megawatts actually all consist of land-based plants. But I think Turkey has as much capacity, even more than that, on the sea. If we can have such plants, we can benefit from the wind potential, starting with the Aegean Sea to Mediterranean and Eastern Mediterranean. Here, the floating plants are mostly seen in northern countries like the shores of the UK and Northern Sea, because these are not that deep seas. Unfortunately, that's not the case for the coasts of Turkey. They get very deep instantly, especially in the Aegean, where we have favorable winds. So we need to have those turbines and the technology in place. Unfortunately, that technology has not been commercialized yet. There are exhaustive studies going on, but in depths higher than 50 meters, it is not possible to have a turbine and install a plant in depths higher than 50 meters, but we're going to see them soon. Actually, there was this tender for over-the-sea plant, not through floating turbines, but turbines that would be placed on the seabed. The world is progressing there, and we see steps in Turkey when the actually floating plants are commercialized. We're going to see many examples of them in Turkey too. Thank you very much, Professor. I would like to ask Professor Kadri this question as a person working on secondary energy. Well, generation is okay, but storage is one of the biggest challenges. Does ENDAM conduct any study in terms of storage? Yes, we have plenty of them. Hydrogen storage, well, this is a chemical substance. I didn't elaborate there. We have actually an approach about the generation of hydrogen with electrolyzers, because here we require significant amount of energy. Catalyzers actually is studied a lot in terms of separating hydrogen and oxygen. And here you need to purify the hydrogen, there are carbon dioxide and other gases inside, including oxygen. So you need to use atomic level filters where molecules can go through and purify hydrogen. We have ongoing studies, practices for that. Another issue is about the chemical storage of hydrogen. And this is a very important area. This was popular back in 2005, 6, and 7. I studied that. Another professor, another colleague of mine, Professor Tayfun, also studied that. Storing hydrogen in metal cells is another method. Last but not least, using hydrogen as a battery, especially alkali ones, can be possible. It's an anode substance. You have nickel hydroxide on the other side, and there's this component storing hydrogen. So hydrogen is actually a very versatile source of energy. Here we can generate we can produce general natural gas and give it to the grid. But if you use hydrogen, you actually prevent the gas from giving much harm, as you do not use carbons. We have many studies within NDAP on them, but I did not refer to them much. Wonderful. This was an important for me as I focused on secondary sources. Hopefully I have been accelerated with your inputs. I'd like to thank each and every one of you for your contributions. Hopefully, we are going to see each other in other events. We look forward to seeing you again, dear professors. Good evening. Thank you. Bye-bye.